Hey guys, so for today's video, we won't build anything in particular or won't be showing what I built, but rather I'll try to talk to you guys about the process that occurs in the computer. So normally when using embedded system have really low memory constraints. So most times you have to do some low level coding. So understand how the computer performs some operations will help you along your embedded system journey. So for this video, my friend Steve Emmanuel will explain how computers handle floating point numbers. So why am I making this video? I started making this video because my lecturer gave me an assignment on this particular subject, how computers handle floating point number, and it's quite complicated. So I want to share it with you guys so you guys can also learn about it. So before I invite Xavier, let me give a bit of gist about Xavier. Xavier is a really cool guy. He's really good with hardware design. He does a lot of PCBs. I'll leave a link to where you can contact him on LinkedIn and other social media platforms. So now let's get to the video.
So for today's lesson, we're talking about floating point numbers and basically how computers sort of manipulate floating point numbers. Now, I'm quite sure some of us might be intrigued and ask ourselves how does all of this drama begin to happen? Because imagine randomly opening your calculator, or say for those of us that are programmers, and you have two values that have, of course, decimal places. So because those values are not like the typical integers that the computer can ordinarily just manipulate and solve, for floating point numbers, it takes a bit of tool. Right. So for the purposes of this explanation, I'll be mentioning a few things that will be preparing or setting the ground up for whatever it is we're going to be talking about. So first of all, we'll be talking about what are floating numbers, right? Floating point numbers. Then we'll talk about some of the standards from IEEE 754 for floating point numbers. We'll be talking about some terms like normalization. Also, we'll be talking about complement. Then along the line, there are some few terms I'll be mentioning, which are necessarily the sine, the mantissa, and the exponent. Now, the first question, what are floating point numbers? So floating point numbers are values necessarily that have decimal places, or rather, to simply put, numbers that are decimal fractions. So a typical example could be 2.58, another example could be 4.03, and the likes, like that. So for arithmetic operations, which could involve multiplication, addition, subtraction, and division, the way the computer sort of handles these values, because the computers basically work with ones and zeros, as most of us already know, right? So the first thing that has to happen for the computer is it has to convert whatever value it is that you have in decimal place to binary form. That is the only way you can begin to sort of manipulate those values, right? And typically, if you'd have a computer that say 32-bit, what that of course typically means is that how the computer processes information is in it gets its data is in form of 32 bits of data, right? So which means you have 32 address lines that the computer typically uses, or gets information from the RAM to process whatever it is that it does. So I'm going to be giving a very simple example. So let's say we want to, for this purpose of explanation, let's say we want to add 2.58 and 4.03. We want to do the addition of this. So first things first is we're going to convert 2.58 to binary form and convert 4.03 to binary form. So to do that, of course, I'm going to be using a more simplified format. So I already know that the standard for in base 2 is 0, then you have 1, then you have 2, you have 4, and you have 8, right? And so looking at this, if I need to get a 2, necessarily, in fact, what this already here means is I have 2 raised power 0, I have 2 raised power 1, I have 2 raised power 2, and I have 2 raised power 3, right? So a 2 would simply just be 2 raised power, which is a 1 and a 0, right? So if we are taking this in 4 bits, it means this will be 0, 0, 1, 0. So I've converted my 2 to base 2 already. Now, for the 0.58, the technique of converting this is very simple. You just take the value and keep multiplying by 2 until you reach the point where you get a 0. So what that means is 0.58 times 2 will necessarily give me 1.16. So I'll write down my 1 and then bring out the 0.16 left. Now I'll multiply this by 2 also, and I would have 0.16 times 2. I have 0.32, as you can see in my calculator, and I'll have 0, and I'll bring my 0.32. I multiply that by 2, and I would have 0.32 times 2. I'll have 0.64. So I have 0, and I write 0.64 times 2. I have 0.64 times 2. I have 1.28. So 1. I write my 1 and carry my 0.28 times 2. And then I have 0.28 times 2. I have 0.56. So I have my 0. I have my 0.56 times 2. And here I'll have 0.56 times 2 to give me 1.12. So 0.12. So I have 0.12 times 2 to give me 0.24. So I can have my 0. Now, in some cases, the values might have a terminal end. Some other cases, it can keep going on and on and on and on. Right. So, and that already, of course, defines how accurate, the computer can get. So, the more the values the computer can already sort of generate, the more it tries its best to get the accurateness of whatever data. So for instance, you are processing things like images, or for people that develop games, you want to get that deep level of accuracy, which is how you can keep going. So for the purpose of this explanation, we'll just stop here. So what this typically means is I will have 0010 point. I can start writing down my values, and in this case, I will start from bottom to top. So it will be 1001010. Now, mind you, like I said, it can keep going further and more along the line. Now, if this is my answer in base 2, what that already means is that I can simply pick up this value. Okay, so let's take the 4.03 and try converting that to base 2 also. So for 4.03, following the same trick, it means I have 4, I have 0, and I have 0. So this will be 0100. So to convert the 0.03, we'll follow the same method times 2. And then I would have 0.03 times 2 should give me 0.06. So I'll write my 0. Then 0.06 times 2 should give me, this times 2 should give me 0.12. So 0.12 times 2 should give me 0.24. So I can carry down my 0.24 times 2. This should give me, times 2 should give me 0.48 times 2. This should give me 0.48 times 2. This should give me 0.96, and times 2 should give me 0.96 times 2 should give me 1.92. So 0.92 times 2. So I can carry the 1 right here, right? So at this point, we can keep going on. So this should give 1.92, right? So mind you, all of these values are not necessarily usable because I already used them in my multiplication. So these are what I'm going to be taking. So like I said, you take this from top to bottom, and this would give me 0.00001. Right, so it means from here I can have 0.00001 in base 2. So these are my two values, right? Now simply, since I have is an addition, I can simply do the addition of both of them. So which will give me 0, 0, 1, 0 point 1, 0, 0, 1, 0, 1, 0 plus 0, 1, 0, 0 point 0, 0, 0, 0, 0, 1, and then I can attach a 0 at the end there. So this should of course give me 0. Now 1 plus 1 in base 2 of course will be 10. So I can write down my 0 and carry down my 1. Then I have 1, 1, 0, 0, 1 point 0, 1, 1, 0. Now, moving on to the next thing is how does the computer save these values, right? The 2.58 that we've converted and the 4.03 that he has converted before it does this arithmetic calculation that we've just done. So typically for the 2.58, now this is where some of the explanations I'm going to be calling in. So first of all, the standard of IEEE 754 states that for a 32-bit float, but for a 32-bit floating number, you would have the first bit. So 1 bit will be for the sign, right? You would have 8 bits for the exponent, and then you have the remaining 23 bits for the mantissa. And what that necessarily means is that like I use this very simple formula that sort of provide also, so which is 1.m times 2, of course, raised to the power e, which is the exponent, minus 127, right? So with this formula, I'm going to be using this formula to show how all of this floating point conversion begins to manifest itself. Now, this aside, let's just hold this thought process in place. Now, there's another term called normalization, which is going to be very crucial in doing this explanation. Now, in normalization, what it just simply means is the point where you have your decimal point, or where the decimal fraction actually signifies itself at the most significant bit, which is a 1, right? Now, what this means is, imagine I have a situation of 0, 0, 1, 0, 1, 1, right? Now, let's say 0.101. So what normalization is typically just saying is how many times do we have to move this decimal point. That is essentially what normalization is. So in decimal places, it is called standard form. But when it comes to in base 2, you have it as the normalization, right? Which is, still follows the same logic. So now for normalization, you basically have 2 types of normalization. So you have the implicit normalization and you have the explicit normalization. So for the implicit normalization, what that just explains is that you have to move your decimal fraction to the point before the most significant bit. So in this case, our 1 is our most significant bit here. So it means my decimal point has to come before the 1, or rather come after the 1, right? So I will have my decimal point. That's what implicit normalization means. But for explicit normalization, it means my decimal fraction has to come before the 1, which will be at the back. Let's put it that way, at the back of the 1. That is necessarily what I mean. So in this case, in implicit, what this would be 001.011101. While for explicit, it will be 00.1011101. This is what it would be for explicit normalization, right? So now, but because of precision and accuracy, IEEE has set the pace that we should easily follow implicit normalization for solving floating points like this. Now, the final term I would like to explain also is something called the complement. The complement is quite interesting because I don't know how many of us have ever thought of how computers handle negative values. So when you typically have your -1, -2, the computer doesn't know what -1 is or what a -2 is. It uses something called complement. Now for complements, you can either have your 1's complement or you can have your 2's complement. Okay, right? So you have the 1's complement and you have the 2's complement. Now, what the 1's complement simply means is do the inverse or do the complementary of the negative value, and whatever answer you get, that is now the ones complement. But when it's a twos complement, you are necessarily adding 1 to the complement of the negative value that you had. Now, I'll give you a typical example. If, say, for instance, I have -6, right? The computer doesn't know what -6 is, right? Following the analogy I was also giving, because think about it, how do we want to convert -6 into binary form? I know the thought process might be, okay, since it's 6, I can convert 6 to binary form and then just add a minus sign, but that's not how it works, because even that minus, the computer doesn't understand what a minus sign necessarily means. So what it does, or rather what is in principle used, is that I'm going to convert 6 to base 2. Now, to convert 6 to base 2, what that would simply be would be 0, 1, 1, 0, right? So, I mean, you can do the conversion yourself, and this is what you should get: 0, 1, 1, 1, 0, 1, 1, 0, right? Now, if this is what I would have for 6 normally, if I convert 6 to base 2, when I do the complement of 6, what that will mean is that every single place I see a 0, I call it a 1, and any place I see a 1, I call it a 0. So what this will translate to be 1, 0, 0, 1. This is what is called the ones complement. But in the case of the twos complement, what that would be is after converting this to 1, 0, 1, I'm supposed to add a 1 to this value, right? So what this would simply be would be 0, I carry 1, and then this becomes 1, 0, 1, 0. So this will become the twos complement. So this is what it necessarily translates to. And we'll be needing these values in the course of moving forward, right? So just to make it simple, I'm going to draw a simple table for the complement. So imagine I have 0, 1, 2, 3, 4, 5, 6, 7. Right? Now, I can also have -1, -2, -3, -4, -5, right? So I can have here -6 and -7. Now, the reason why we are doing it is because of the 6 of the mantissa, like I already, sorry, for the exponent, like I already mentioned, because remember I said that the exponent is, according to IEEE, is 8-bit, right? So what that simply means is that if you do 2 raised to 2 to the power of 8, what you'd simply get is 256, right? So what that means is that you can have 256 different combination of values, right? So what that translates to is that I can have a value between 0 to 255. That's what it simply means when you see 8 bits. If it's a 4-bit, what that simply means is just 2 to the power of 1, that's 16. So you can have 0 to 15. Now, the reason why you're having that is because 0 is inclusive as part of the numbers that are sort of recognized, right? So, yeah. Now, following that same logic is what we are displaying here, right? That since it's 8-bit, so we are having 0, 1, 2, 3, 4, 5, 6, 7, right, as what we are considering. Now, also, we're also considering the same thing on the negative side, right, of our of the table that I'm going to be drawing right now. So, from this table, right, we are going to be computing the different conversions into binary form, right, to help ourselves in finishing up with the floating points calculation. So for 0, I would have it to be 0, 0, 0, 0, right? For 1, I would have it to be 0, 0, 0, 1. For 2, I would have it to be 0, 0, 1, 0. For 3, I would have it to be, sorry, let's put the arrow marks there to help us identify it. For 3, I would have it to be 0, 0, 1, 1. For 4, I'll have it to be 0, 1, 0, 0. For 5, I'll have it to be 0, 1, 0, 1. For 6, I'll have it to be 0, 1, 1, 0. For 7, I'll have it to be 0, 1, 1, 1. Right? Now, for -1, I would have it to be, so now, just like I said, so for -1, we're going to be doing the complement of 1. And the complement of 1 would be 1, 1, 1, 0. The complement of 2 would be 1, 1, 0, 1. The complement of 3 would be 1, 1, 0, 0. The complement of 4 would be 1, 0, 1, 1. Complement of 5 would be 1, 0, 1, 0. Complement of 6, which we've done before, would be 1, 0, 0, 1. And the complement of 7 would be 1000. Right. So now that we have these values, we can now go to computing our values for showing the addition of what we have here. So recall that the question at hand is 2.58 plus 4.03. Right? So 2.58 plus 4.03. Now, mind you, we already said that 2.58 converts to binary form in what as 0010.1001010 into base 2. So for us to follow what the IEEE has said, of course, this first is the sign bit. Now I will have my exponent to be in 8, of course, 8 bits. So that is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, right? And then my mantissa can go on as long for 23. These are 3 bits, like as they said. Now I'm not going to draw everything, of course, because I might not necessarily use the whole thing. Now, so let's say 1, 2, 3, 4, 5, 6, 7, 8. So this is our exponent. I'll just put a double slash to highlight that that is the point of the exponent. And then here I have my mantissa. And I'm going to recall the formula again that says that you have plus or minus 1.m times 2 to the power of e minus 127. Now, recall I once mentioned that the exponent is 8 bits, right? So usually there's a term to something called a particular term called bias. Now, in bias is when we are trying to convert the exponent value from its decimal form into ones and zeros. That's what the bias is. And because it's 8 bits, that is the reason why you are seeing we are doing this minus 127, right? Because for those of us that are very familiar with programming languages, if I call a particular variable an unsigned variable, or I call it a signed variable, when it's an unsigned variable, what happens is that it only takes the positive value. So that means if, for instance, if it's an 8 bit, it will do 0 to 255, right? But when it becomes a signed bit, it means I'm both considering the negative and the positive value. So that becomes minus 127 to plus 127. So that is why you see the IEEE standard gives it to be the exponent minus 127, right? I don't know if that makes sense. Now, this M signifies the mantissa, right? Where this E is the exponent. So this E is the actual exponent, right? Whatever value that you get. Why this other exponent? Let's call it E bar. Right, so that we can easily say that E bar is equal to E minus 127. So, just to make it easier for us to understand. Now, let's come back to our question. So, this is what we have in binary form. So, the first thing we are going to do is do what is called normalization, like I explained to you, which is the moving of the decimal point. So, in this case, our most significant bit is this one. So, I can just move my decimal point just once here, and that will be fine. So, it means I will have 001.01001010 into base 2, right? So it means that since I already have this, now I just check my value. Is this a positive? This is a positive value, right? So it means now according to IEEE, your sign should be 0 if it's a positive value. If it's a negative value, it should be 1. So what this simply translates to is that I can have, since this is a positive value, I will just call my sign bit a 0, right? Now, for the exponent, right? For the exponent, what I can easily do, okay, so for the exponent, what I can simply just do is you count how many times you moved your decimal points, right? So you move your decimal point just once. So what that would simply mean is times 2 raised to power 1. That's because we moved it just once, right? So if I have it to be 2 raised to power 1, I can easily come back here and say, right? So in this case, we have our 1, right, as the exponent. So what that simply will be is that this is it, right? So recall that E minus 127. So if I make each of the formula, I will have 1 plus 127, which gives me 128, right? So if now you have to convert the value into binary form. So to convert this into binary form, I already know that my 2 raised to power 7 would give me 128. So I can call that a 1. Then every other value down to when 2 is raised to power 0, it will be 0. So when 2 is raised to power 6, raised to power 5, raised to power 4, raised to power 3, raised to power 2, raised to power 1, raised to power 0. So this will be 0, 0, 0, 0, 0, 0, and 0. So I can transfer this into my exponent, which becomes 1, 0, 0, 0, 0, 0, 0, and 0. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that is what our exponents will become. Now, for the mantissa, every value after the decimal point becomes your mantissa. So we just rewrite all what we have here into this. So we have 0, 1, 0, 0, 1, 0, 1, 0. Okay, so we've done for the 2.58, we've concluded for the 2.58. Now let's go to the 4.03. Now for 4.03, what that would give me, like we already converted, it would be 0, 1, 0, 0, 0, 0, 0, 0, 0, 1 into base 2, right? So just like I said, the first thing we're going to do is our normalization. So I'll move my decimal point twice, 1, 2, where the most significant bit is, which is 1, right? And so what I will have is 1.00, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, times, I move my decimal point twice, so times 10 raised to power 2, right? So again, we'll draw the same allocation table for, which is how the computer sort of sees these values while it's working on it. This is the exponent, this is the sign bit, right? So in this case, you'd have, this is also a positive value. So my sign bit, of course, will be what? Will be 0, right? Now, my exponent is 2. So simply just do, 2 plus 127, and that will give me 129. So following from this, I can easily say, 129 would give me, okay, so 129 would give me 1, this is 128, 0, 0, 0, 0, 0, 0, 1, right? So this is the exponential form. Now, you can take the time to convert this into binary, and then you see that you get the same answers I'm getting. I'm just following the particular system to do my conversion, which is, I feel like, is way easier. So writing this, I'll have 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then 1, right? And then the rest of the values become my mantissa. So that becomes 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and then the numbers can keep going on and on and on. Now, the longer your values of mantissa, the higher or the increased level of accuracy, like I said before, that that grants you, and which is the other reason why, I mean, not to diverge, but is also the reason why we now have even 64-bit float point table, right? So in that case, rather than having it to be minus 127, you have it to be minus 1023, right? That just changes. So everything just increases, but it still follows the same format. And all of this is just to help increase the level of precision and the level of accuracy that the computer can sort of grant to you. So technically, why I'm doing this is because this is what the computer does. So when you have 2.58, this is what immediately it converts it to, right? When you drop your 4.03, this is what it converts it to. And then it does the sum of these two values and then gives you the final answer. So, but for in our own case, we've already done the addition of these two. So our final answer easily was, what was the answer we got? So we got 0110 point, all of this. So we have 0110 point 100 1100. So if to arrange this, of course, I have to move my decimal point, I think twice. So this will be 1, 2, which gives me at that point there. So this will be 1.101 0.001100 times 10 raised to the power 2. Now, you might wonder why we even bother doing the minus sign. Now, imagine that the 1, let's say for instance that you had 0 point whatever. Now, you can choose to either go this other way, because imagine that you had to take your decimal point in the right direction. What that would mean is that you will be reading in negative sign. So imagine I move it twice in this direction, it will be -2. Now in that case, if you do -2 plus 127, that gives you a reasonable value that you can now use for your calculation. Right, so that is it technically. So this is the answer. Now I can now already sort of put this in my table also. So is a positive value, so I can call this 0 as the sign bit, and then for the exponent, we already have 2, so we can just use the same thing we had from this table, which would be 1 0 0 0 0 0 0 and then 1, which is exactly what was here, which is the exponent. And then on this other side, you have the mantissa. And the mantissa will be every other thing here. So this will be 1 0 1 0 0 1 1 0 and 0. So with this, we've come to the end of the lesson. Now I think moving on, we can use the simulation software to show you this whole analysis that has been done very easily using some very few scripting codes just to portray all of these calculations that happen. So the next time you punch your calculator, this is really what happens in your computer. Thank you.
So this is the simulator here. Basically shows you the sign, significand, and the exponent. Anytime you perform a calculation using floating point number, so you can try some random number. You can also use it to confirm your calculation. That's a 5.46, 2.49, 2.49. I can choose the sign I want to use, whether it's plus, minus, or divide. So if I want to add it to number, it gives me the number, shows me the sign, significant, exponent. So that's all. Hey guys, I hope you enjoyed the video. If you have any question about the floating point number system, how they work, how the computer handle it, you can always post in the comment section. I'll forward your question to Xavier and answer them. I'll respond back to you guys. But if I know the answer, I can also respond to your message in the comment section. And if you love the video, please don't forget to hit the like button and subscribe. And also hit the notification bell, so whenever I post a new video, you'll be notified. Thank you guys for watching, and see you in my next video. Bye.